Hi, I'm Matt McClintock, and here is my video report for Lab 1 charged tapes. The purpose of this experiment was to observe how a charged strip of tape interacts with other neutral and charged objects. We were then asked to determine the number of excess or deficient electrons on one strip of tape. Here is a quick preview of the major results from the experiment. I found that two charged tapes repel when brought close together, and the tapes are positively charged with a magnitude of 7.93 times 10 to the negative 9th coulombs. The number of deficient electrons was determined to be 4.96 times 10 to the negative 10th electrons. Lab 1 covers all the major physics principles taught in lecture so far. They include Coulomb's law and hence the equation for the electric field of a point charge. During the experiment, the equation is manipulated to determine the tape charge. Newton's second law was also used to calculate the gravitational force on the charged strip of tape. On the right are the Coulomb and fundamental charge constants. Before the experiment, strips of charged tape had to be prepared and measured. My tapes were all 0.2 meters long, 0.02 meters wide, and had a mass of 0.0002 kilograms. The length of an atom, approximately 1 times 10 to the negative 10th meters, was necessary for the last part of the experiment. I observed that a charged piece of tape repels another piece of tape, which matches the principle that like charges repel and opposite charges attract. The tape, regardless of positive or negative charge, will be attracted to neutral objects, in this case a hand or book, because it induces temporary dipoles on the object. Most importantly, the charged tape was attracted to a negatively charged pen, showing that the tape has a positive charge by Coulomb's law. We made some assumptions to simplify the experimental model. The mass of the clear Scotch tape was estimated at 1 gram per meter. Additionally, each tape was said to have the same net charge concentrated at the center of mass. Only the gravitational and electric forces were accounted for in the calculations because they are the most prominent forces. When calculating the number of atoms on a piece of tape, atoms were said to be arranged in a perfect lattice structure to simplify the expression. The system in the experiment was tape B, while the surroundings encompassed everything else, including tape A on the bottom. When performing vector calculations, establishing a coordinate system is essential. In this experiment, the positive x direction was assumed to be pointing to the right, while positive y was pointing up and positive z was pointing out. Creating the experimental model involved preparing two strips of tape by ripping them from a base layer of tape stuck to a desk or table. While handling the first piece of tape by its ends, stick it to two books so that the middle sags between them, as shown in the diagram. Repeat the preparation process for a second piece of tape and slowly hold it underneath the first until it begins to float. This is simulating the electric force of the bottom tape A on the top tape B. Finally, measure the separation distance with a ruler. I determined mine to be 0.017 meters. Here are the calculations I performed for the mass, the magnitude of the gravitational force, and the magnitude of the electric force. For the mass, I simply used unit conversion procedures to get from meters to kilograms. The gravitational force was calculated by multiplying the mass quantity and gravitational acceleration constant. The electric force had to be the same magnitude to achieve equilibrium. Next, I found the charge on the floating tape B by manipulating Coulomb's law equation to isolate Q sub B. When finding the ratio of deficient electrons to atoms on the strip of tape, I first determined the number of atoms by dividing the tape area by the atom area. I then found the number of electrons by dividing the charge of all electrons on tape B by the charge of one electron. Here is the GlowScript program I wrote for this lab. Like the experiment, it models the two charged tapes as point charges. The force of gravity on tape B was modeled with an orange arrow on line 27 after calculating the weight of the tape. Using the function E-force on line 40, I modeled green arrows in the display window that represent the electric force on both pieces of tape. I wanted to emphasize the presence of an equal and opposite force on tape A due to Newton's law of reciprocity. After performing the experiment and modeling the scenario with GlowScript, we can conclude that tape B reaches an equilibrium position at certain separation distance because the gravitational and electric forces balance. Additionally, there was no discrepancy between the calculations from the physical experiment and those in the GlowScript code. However, a likely source of error was handling the charged tapes too much before holding them close together. Additionally, measuring the separation distance with a ruler was difficult because I was already holding one piece of tape with both two hands. The first positively charged tape could have lost some of its charge to electrons in the atmosphere as I was preparing the second. If electrons had a positive charge and protons had a negative charge, the strips of tape would still be attracted to neutral objects due to the induced dipoles formed in these objects. Contrastingly, the negative charge tape would be repelled by the pen or another tape of the same sign. It is important to handle the charged tapes as little as possible to prevent transferring electrons from your hand and potentially reducing the net positive charge of the tape. The reduced charge and hence reduced electric force will decrease the separation distance between the two tapes.